Hello everyone, my name is Elizabeth Post, and this is my presentation for Project 5, JAC Compiler Optimization. I chose to utilize the toolchain provided by Dr. Bond and the authors. This was due to a number of factors, mostly for reliability of the outputted files and for ease of use. Additionally, when my toolchain was utilized, the program was too large to fit into the VM emulator memory, so while there was certainly a lot of optimization to be achieved, I was unable to verify that the output I was getting would be correct, and I didn't want to have to make optimizations twice if I had made an error in my toolchain. Push local and add were among the most called functions, and looking at add, it seemed a more approachable task, so I began with that one. I ran the original code in the VM emulator, and I realized that the first value popped off the stack was being stored in register 14, and then that register was being used to set D later. This was unnecessary because when we call the popd command, we set the value in M in the AM equals M minus 1 instruction, and therefore we can directly access that data. So instead of storing the top value of the stack in a register 14, I rewrote the assembly to pop the first value into D and hold it in that register, and to pop the second value into M. I was then able to directly add the D and M registers and store in D, which was then pushed onto the stack. This resulted in a 23% decrease in the length of the add subroutine and a decrease of 9,335,748 clock cycles in 0.153 seconds. Not a bad improvement for the modification of one subroutine. Next, I modified the push local command. Once again, after watching its behavior in the VM emulator, it became apparent that it was erroneously saving values in registers, instead of just utilizing the values directly once they were in the D or M registers. In this case, R13 was being set to the sum of the values in the R13 and the R1 registers using the D registers, when we could just grab the second value directly out of the A register, after of course setting equal to the M register. This decreased the length of the instruction push local by 28% and saved 26,601,780 clock cycles, which brings our total down to 436,778,000 clock cycles, and saving nearly half a second of simulation time. Altering this instruction had such an enormous effect because it optimized not only push local, but push argument, push this, and push that. A few days later, I took another pass at this section of code because the modification had had such a profound effect, and found another instruction that could be squeezed out. Just by decreasing this section by one instruction, clock cycles decreased again by 6,650,000. After modifying push local and seeing how it could be applied to the other push commands, I started looking for areas where one change could be applied to other subroutines as well, and I came across the comparison subroutines. Similar to push, we were storing items in R14, something that required getting the value in M, setting it to D, and then resetting the M register with the value in 14, when I thought we could just keep the top value in the D register and the second value in the A register. This caused the first compilation issue I ran into. Keeping the value in the A register caused a segfault to happen when running the CPU profiler script. This was because it was unable to write to RAM when the value in A is negative, so the value we were popping needed to be placed in the M register instead of the A register. This had the added effect of getting rid of an instruction because I no longer had to set A. This decreased the length of each subroutine by 18% and removed a total of 6,508,452 clock cycles. Next up, I modified the binary operators assembly. I realized that the and or instructions were erroneously storing information in R14 when they could just be kept and accessed in the D and M registers. Modifying and removed 1,944,368 clock cycles, and modifying or removed 360,000 clock cycles. Inline return was an obvious candidate for modification given its length at 57 instructions. This turned out to be a more challenging task than I had anticipated and was only able to squeeze out 4 instructions, which is about a 7% decrease in subroutine length. I did this by again avoiding storing instructions when we could just leave it in the D and M registers. This resulted in a decrease of 2,581,303 clock cycles. The last assembly code modification I undertook was to pop indirect. Similar to push commands, we set a register equal to the address of the segment at the value of n. I realized that we were storing the top of the stack in a register for when it was needed later. So if I just changed the order of instructions and just popped when we needed the value, it would cut out having to store it. This decreased the instruction length of the routine by 23% and saved 5,038,293 clock cycles. An area that I did not quite have enough time to get working, but certainly made an effort, were the OS libraries, specifically the math functions. After digging around in the original S2020.jack source code, I realized that cell.jack was heavily relying on multiplication subroutines. Unfortunately, my VM code reading and writing skills is not as proficient as my ability to read and write ASM, so after spending several fruitless hours trying to make modifications, I had to abandon this effort. In total, the optimizations made to the ASM code were able to reduce the number of clock cycles by nearly 60 million, the execution time by over a second, and increase the simulation speed by over 2,550 kiloclocks a second. Thank you so much for listening. Good luck on any finals you may have remaining, and remember to wash your hands.